Welcome to part 4 of Markov chains. Today we're going to do the analysis of Markov chains. It's a relatively long lecture, so I have divided it into several parts, and we will see here the different segments. So I'm going to let you know as we go on. This material is designed as supporting material for our courses on simulation and stochastic optimization, or simulation optimization as well. We will focus on discrete time Markov chains in this lecture, but we will include a discussion of continuous time jump processes as well, which are very relevant, particularly for the simulation course. So the material is divided into two parts. First, the analysis of absorbing states, and secondly, the stationary analysis. Sometimes it is called random horizon or finite horizon for the analysis of absorbing states, and infinite horizon for the analysis of the stationary case. The references that I'm using are the Ross and Taylor and Carlin for Introduction to Probability Models, and I will be referring to this as we go along. If you want to see the details, you can always take a look at the textbooks. So we start out with absorption analysis. And to motivate, let us take a look at the problem of the gambler's ruin problem. A gambler plays consecutive rounds of a game. She has a probability P of winning, and if she wins the round, she wins $1. Otherwise, she loses $1. The total amount of money is N dollars. That's the total amount in all, the game. So the game will end when either she loses or she wins all. And of course, the way that we depict this is visually is by saying, well, if she's got $2, let me annotate so that you could see what I'm talking about. So let's say that she's got $2 at a particular time on the game. So then when she plays a round, either she wins with probability P, and then she will have $3, or she will lose with probability Q, which is 1 minus P. And then she will have $1. So that's the way that we depict this particular Markov chain. The transition matrix is going to be only probability of going to the right, which is P, or probability of going to the left, which is 1 minus P. So these are the transition probabilities. And when we are at the boundaries, so if we are already at, if she has N dollars, then the game is over. She's got all the money and the bank cannot play anymore. So we say that she won. Whereas the other situation, if the total amount of money that she has in the game becomes 0, then she can no longer play. She doesn't have any more money. She no longer plays. And that is the event that we refer to as the gambler's ruin. So what are we interested in here? We're interested, well, first of all, let me just let you know. When I write down exercises, I suggest that you pause the video, think about the exercise, and write the answers on your handwriting. It helps to keep up the pace of the lectures. So I'm not going to be pausing, but I encourage you to pause that. All right, so we denote by tau the total number of rounds in a game. So the total amount of rounds until the game is over. So by definition, mathematical definition, tau is the minimum number of rounds where either her capital wealth is 0 or is capital N, and that's when the game is over. The gambler's ruin is the event that at the final time, she's got $0. That means she lost. That's basically the event of losing the game. For this example, one is interested in calculating the ruin probability, which we're going to define, and we're going to be working on this later, so it's very important that we keep this in mind, is the probability that the gambler loses given that the gambler starts with a capital of $i. So that is the first thing, which is the ruin probability, and it depends on the initial state. And the other one is, the other important quantity is the expected number of rounds in the game. Again, it's conditional on the initial state. So those are the two quantities that we're mostly interested in calculating here. So how do we calculate using conditioning? Well, to do that, I'm going to use my iPad to show you a little bit of the equations, how we do that. So the way that we do that is the following. We first establish some boundary conditions, which are at the extremes, the boundary conditions. And these are just logical conditions. First of all, U0 will be the probability that the capital, the end capital or wealth of the player is equal to 0, given that the player starts with $0. So this is a tautology. This is equal to 1. Now, the U sub n, which would be the probability that the gambler ruined, given that the gambler has already won, well, if this is equal to 0. So we're going to be using this as boundary conditions. Now, we use conditioning in order to evaluate expectations. And what we have is the following. UI is the probability that X tau is equal to 0, probability of losing, given that we start out at I. So what we do here is that we condition, this is also called a first step analysis. So we condition on going from step 0 at I to iteration number 1. In iteration number 1, we can go to other states, J. In general, doing that, when we use the law of total probability, we would obtain that this is equal to the sum over all the possible intermediate states of the probability that X tau is equal to 0, given that X1 is equal to J times the probability of going from I to J. So basically, we're looking at a time number, the first iteration, not the 0 one, but the first one, we landed on another state J, and we're looking at the probability of ruin, so going to 0 from that state J. So that's the way that we evaluate probabilities by conditioning. But suffices to realize that this is nothing but U of J. It's the probability of losing, given that I start at J. So we obtain the equation that UI is equal to the sum of over all the possible following states of Pij times U of J. But now we're going to be using the fact that for this particular chain, we can only just go to I plus 1 with probability P, or we can go to I minus 1, sorry, that's I minus 1. With probability Q. And so this simplifies, and this is just telling me that this will be U I plus 1 times P plus U I minus 1 times Q, except when we're at the boundaries. So this is for all indices I, such that they're not in the boundaries, not 0 or n, because that's when we can go from to right or left. And of course, for the boundaries, we're going to be using these equations. So these are the equations for the boundary. which are the ones that we will use for all the others. So this is going to give us a system of linear equations that can be solved uniquely because we have the boundary conditions as well. So this is what we are, this is where we are now. And so this is how we get this system of linear equations by conditioning. And when we want to look at VI, VI is the number of rounds until the game is over. And then again, we can use the conditioning and we get a similar equation. So applications of this are in insurance companies. Applications can be drug testing, algorithmic efficiency, and many other applications of the gambler's ruin problem. This is a particular case of a random walk. And we, in particular, we use the model to study bike occupation docs for the public bike share systems. So I'm giving the reference that I published with one of my former students. When we look at the absorption analysis in general, so that was an example. So how do we do the absorption analysis in general? We're going to look at the general mathematical formulation and how do we work this out. So I'm going to show you my screen again, my iPad again. Okay, so we have this idea that now there are states, I'm sorry, I need to find the states 1 up to R are transient states. And so these are the ones, the states that are in the set that we call T, which is transient states. The corresponding probability matrix for this particular example has R rows in here. So these are states 1 through R. And because these are transient states, then there's always the probability, a positive probability of transitioning from one of these states outside. So where do we go outside? We're going to call A, capital A, the set of absorbing states. And for this particular analysis, which is relatively simple, for this particular analysis, we're going to assume that the state A, the space, the subspace, is comprised of purely absorbing states. So all of these states have a probability of return of 1 into themselves. So once we get into one of these absorbing states, we don't get out. It's in the case of the gambler's ruin problem, we have 2. Either we stay at 0 or we get absorbed at capital N. In general, we can have several of them. And that's reflected in the fact that this matrix, which we are going to call matrix identity, is basically the identity matrix. It has ones in the diagonal and it has zeros otherwise. And this corresponds to the rest of all the states, which are n minus r plus 1 states. Now, because there is always a probability of going from T, from the transient states to the absorbing states, then this part of the matrix, which we're going to be calling R, is non-zero. So the sums of the rows have to be non-zero, meaning there is a positive flux into one of the absorbing states. We don't know exactly which one, or maybe to all of them. So these represent the destinations are the absorbing states, and this represents that the origins are in the transient states. So the rest of the matrix is a big zero matrix. because from the absorbing states, so this will be the absorbing states, we cannot go into the transient states. From the absorbing states, we only just remain at the transient states. So this is the general formulation, and we're going to see how we write this down in math formulas to be able to do the analysis. So this is basically the model that I just explained with the picture. And so we have the matrix, the transition matrix is divided into 4 submatrices, as I just explained. And the assumptions here that we do is in order to assume, as I said, that the absorbing states are all, that the non-transient states are all absorbing states, and that the transient states are the first R states, and the rest of them are all absorbing states. So I have an exercise for you. So again, you can pause and you can try and figure out this exercise. All the states in A are single class absorbing states. So the transient analysis in the general formulation defines the following. First, the time to absorption. Time to absorption is the first time, discrete time, that the chain is in one of the absorbing states. So my exercise for you, show that tau is a stopping time adapted to the natural filtration of this Markov chain. The other thing that we define is, in general, we want to find a cost associated with a cost or a profit associated with this Markov chain. So for that, we define a function g, which is an instantaneous cost function of each of the states. And so the total expected cost will be wi, will be the total expected cost, which is accumulating over all of the steps. And so it accumulates over all of the steps. And so this is the sum from the n equals 1 from the first step to the end. And we are accumulating the costs of this, the g end. And here we're starting at 0. So basically, this little I here means that we are, means that we are starting at the 0. So this I means that we start at x0 equals I. So that's in general how we define the cost analysis for absorbing states. So the general problem statement asks us to do 2 things. Calculate absorption probabilities. Now we have different absorbing states. So we don't have only 2, we can have many absorbing states. And so for each of the absorbing states K, we can have a different probability of absorption. And of course, it also depends on the initial state. So now the absorption probabilities are going to have 2 indices. We start at I, and we're going to finish at K. And we want to calculate those probabilities. And the other problem that in general we want to do is calculate capital WI, which is the expected cost conditional on starting at state I. So those are the 2 main issues in the analysis of absorbing Markov chains. The example that we have here is an example that my students know very well because it has come up in the homeworks, and we have been using it to illustrate different things when we study Markov chains. So this is the rat, is in maze, and he's located in a starting chamber that has 2 possibilities. He can either go to the right or he can go to the left. If he goes right, then after walking several minutes, in this particular case, after 1 minute, he's going to return, no, after, sorry, 3 minutes, he's going to return to the initial chamber, so the starting chamber. If he goes to the left, then he's going to find, after 1 minute, he's going to find a fork on the path. And in this fork, he can either go right, which is like the green path in here, and he goes to the exit, or he can go to the left, which is the blue path here, the blue way. And if he goes there, then eventually he's going to go back into the initial chamber. So that's basically the way that the rat is moving on the maze. Obviously, every time that the rat is choosing not the exit path, Theseus is going to come back to the initial state, and it's going to go over and over and over until finally, when he decides to come this way, then he will exit. So that's the absorbing state when he goes to the exit. So again, an exercise. For the problem of Theseus the rat, specify an appropriate model for the chain. And how would you define the instantaneous cost so that the expected time to exit is given by WI? I suggest that you pause a little bit and you try to figure out with our notation, how does that apply to this particular example? We're going to see now the general solution. The general solution approach is by conditioning, also called the first step analysis. And of course, when we use Markov chains, we're always using conditional expectations and the law of total probability. That's the main tool of analysis in general. So the boundary conditions are going to be depending on each other problem, and in general are very straightforward to find out, the same way that we did before. So what we're going to do is that we're going to find out how do we actually solve this problem. The first thing that we're going to do is that we're going to do the first step analysis, which is basically conditioning on the first step on the Markov chain. At n equals 0, we are at state I. So at n equals 1, we're going to go into another state that we're going to call J. This is what is basically the first step analysis, is to go one step further and then look at the future from the state J. Now, we can have several, so if we do that, conditioning on that state, we get that this is equal to, at n equals 0, we have a cost of G of I, which is that first term in the sum, because we are given the fact that x0 is equal to I. And then we have all the possibilities for J. So the state J can be one of all the possible states in the state space. So we have the sum over all of the possible states where the process can go to, of the expected value of the sum from n equals 1 now up to tau of G of xn, given now that x of 1 is equal to J, and that, of course, multiplied by P I J. So we're starting now at n equals 1. This is first step analysis because we have already taken into account the step n equals 0. Now, we need to notice, when I mentioned the boundary conditions, we need to notice that there in the model, we have two possibilities. Either this next state J is in the absorbing set of states. If this is in the absorbing set of states, what happens is that tau is equal to 1 because we're basically done. Absorption has happened. And absorption has happened at n equals 1. also the boundary conditions will be that we know G of J for the absorbing states. These are generally well known, as we have done in the other examples. So we would know that one. And the other possibility is that J is in the transient states. So for the transient states, we have not arrived at the absorption. And so we know that the absorption time will be bigger to 1. There are still some steps to go. So when we do that, we obtain this equation. Wi will be, this is for I equals 0. And then we're going to divide into the two possibilities. So either we go to an absorption state, and then the corresponding cost will be G of J times Pij, or we go into a transient state. If we go into a transient state, we need to express what this probability is, this expectation is, and it will be, again, the expectation of the sum going from n equals 1 to tau of G of xn, given that x1 is equal to J times Pij. So I basically just repeated the same expression that we had before, but I've now divided into J being in A or J being in T. So it's either absorbing or transient. So what do we do with this? Now we realize that this expression, we can use the trick of shifting the time index because the process is Markovian. And so this is the same as the expected value starting at 0 of G xn given x0 equals J. So that corresponds exactly to Wj. And that's how we will obtain the final formula, which is Wi equals Gi, the term corresponding to n equals 0, plus the term corresponding to going immediately into absorption, plus the term of continuing into transient states. And this is the final expression that we find in order to find the solution for the absorbing states. So this is the final slide that we have with the results that we just discussed. So that's the exercise. If this is a continuous, suppose that X is a continuous time Markov chain or a semi-Markov process. At the state I, the process spends a random time with some distribution Gi, which is independent of the past. In the case of CTMCs, continuous time Markov chains, this distribution is exponential. In case of semi-Markov processes, it could be a general distribution and it could have memory. Tilde xn is the way that we denote the embedded discrete time Markov chain. And so the exercise is to show that the absorption probabilities for a continuous time process, whether semi-Markov or continuous time Markov chain, are the same as those of the embedded discrete time Markov chain. The importance of this is that if we're dealing with continuous time, it is enough to look at the embedded Markov chain and find the results for the discrete time Markov chain and do the analysis as we just did before. And that also carries on for the continuous time. For the expected time to absorption, it is a little bit more elaborated. So we're going to go through it in detail. If x of t is either a continuous time Markov chain or a semi-Markov process, then of course we're talking about continuous time. The embedded discrete time Markov chain has a transition matrix P, which is given in equation 1 before. And we are going to call Tn the holding time. So as we have seen, the holding time satisfies that given that the state currently is I, it has a distribution Gi. So the holding time has different distributions when we are at different states. We're going to call 1 over Vi the mean of the distribution Gi. And An is the actual time of the nth jump of the process. And that's why it is given by the sum of all of the holding times that have happened up to time n. So if tau is the absorption time, on the discrete time Markov chain, then the continuous time to absorption for x of t will be the expected value of capital A sub tau, which is the actual epoch of the transition where the process is absorbed, and then given x of 0 equals 1. Now notice that this is x parenthesis 0, it's not x sub n 0, because this x at 0 is denoting the initial state of the continuous time process x. And the exercise for you show that Wi satisfies this recurrence. And I suggest that this is time for coffee. Just take a break. Now we're going to go into long-term stationary analysis. So we finished the absorption analysis. The long-term analysis is basically looking at a different type of problem, because now we're going to have recurrent states all the time. In this example, again, I like to motivate with an example. It's an inventory example. Suppose that you supervise the sale of apples at your shop. When the price that you charge is theta, the demand for apples on day n is an integer valued random variable dn of theta. You order k apples at closing time if you're out of stock. So you sold all your stock, and they're delivered the next morning before you open your shop. So if xn is the number of apples in stock at day n, the number of apples that you have at day n plus 1 follows this recursion. The number of apples that you can sell is either the total demand or your total stock, depending on which is the minimum. Because if you have demand which is above the number of apples that you have, you cannot sell more than what you have in this example. And of course, at the end of the day, you're going to have a number of apples, which is k, which is the replenishment, if the demand at that day was bigger than your inventory. And then you asked for more. So for the next day, you start out with capital K apples, which is the maximum amount of apples in your stock, in your shop or in your store. So the exercise is to show that if the consecutive demands for apples are IID for given theta, then xn is a homogeneous Markov chain. And the second exercise is to show that if the probability that the demand be I apples is always bigger, it's always possible to have a demand of I apples, then all the states communicate and thus they are recurrent. So we have a recurrent Markov chain. So the instantaneous profit from the sale of the apples in day n, on a particular day n, is the following. We call that R for revenue or profit. So the revenue at day K is going to be theta, which is what you charge per apple, times the number of apples that you sold. As we mentioned, you are selling only the minimum between the demand and the amount that you do have on stock. And so you have so it's theta times the number of apples that you sold minus C times the number of apples that you bought. Now, in the case that the demand was bigger and you were out of stock, you're going to be ordering capital K apples, and you're going to be paying C amount of dollars for each of the apple that you asked from your supplier. So that is basically what we have as two equations. The one tells us what is the dynamics of the system, and the other one tells us how does the revenue move in time. So the goal is to determine the best value of theta, the price that you're going to be charging per apple, in order to make a profit, assuming, of course, that the demand for apples will be decreasing in theta. If you want to charge too many dollars, then you're going to get less and less people wanting to buy your apples. But if you put your price too low, you might end up having a loss if you have to pay more dollars per apple to your provider than the amount that you can charge for the people. So that's the typical optimization problem that we have in inventory examples. The long run average profit is defined as, well, capital R, because the total revenue. So the total, the long run average profit is the limit as n tends to infinity of the average. So this is a time average. This here is a time average. You're taking the revenue that you get day by day by day by day by day, and you're dividing by the number of days to get the profit per day. So it's the rate of revenue. And when you take the limit as n tends to infinity, then you're going to get the long run average profit, which gives you an idea of how your shop is doing, how your particular enterprise is doing. So this is the motivation. And in this module, we're going to be studying the conditions, or in this section, we're going to be studying the conditions under which such long-term averages are well-defined, and we provide the summary of the analysis tools so that we know how are we going to be able to take a look at that and analyze that. This is, as I said, important for both my courses, the simulation course, as well as the optimization. So we start out with regular Markov chains, limit probabilities. What does that mean? So a probability matrix is called regular if there is an integer such that, I'm going to say this in English, such that every state is accessible from every other state in at most n bar steps. So that's what it means, that you have, say, 10 steps. In 10 steps, it doesn't matter where you started, it's possible to reach every other state. And that's called a regular probability matrix. So in the case of regular transition matrix, there is a limit. The probabilities Pij to the n, remember that Pij to the n is the probability of going to state j, starting at state I in n steps. That's what it means. But we also saw in the previous modules, the previous sections of this module, we also saw that this corresponds, in the case of finite Markov chains, finite state space, this also corresponds to the transition matrix to the power of n. So we can use matrix algebra. or we can understand it by matrix algebra. So what this means is that as we take more and more powers of that transition matrix, which means, we take longer and longer and longer, there is a limit, and the limit is independent of the initial state. So this is very important. The limit of these probabilities are independent. So basically, as a probability matrix, it converges to a matrix that has the same, or the rows are the same, they're repeated. That's what it means. It's independent of I. That's the limit. So starting with this, okay, well, there's an exercise for you. So again, you can pause and you can try to solve the exercise. So the Markov chain with regular transition matrix has a single positive recurrent class. Okay, so the interpretation of those limit probabilities is very important. The quantity pi I is the actual expected fraction of time that the process is in state I in the long run. And to prove that, we define this quantity, which is exactly the expected fraction of time that the state is at I. So we use this notation, indicator function, that the state is visiting the particular state I. The chain is visiting state I. And we add up, we count 1 every time that the Markov chain stays or hits or visits state I. So we count all those visits and we divide by the total number of steps, and that's going to give us the expected fraction of time that the process is indeed at state I. So when we take the limit, when we consider this expectation here, again, we can calculate that expectation using what we are always doing. We're going to condition. We're going to evaluate that expectation in terms of a conditional expectation and given what the first state is. And so this is going to give us this quantity. So this is going from state x0, whichever state that is, into state I in k transitions. So when we do this, we realize that by the theorem that I showed you before, by the result that we had before, this limit converges to pi I, which is independent of the initial one, as k converges to infinity. And so we know that this quantity here, so this quantity here is going to converge to the pi I. So now we have 1 over n from k equals 1 to n of quantities that all of them converge to the same number. That is a Cesarov sum, and we're going to be using a result that is well known, that if you take the average of these random numbers and they all converge to the same number with probability 1, then the whole sum also converges with probability 1. So that demonstrates that this number 5, which we have defined as the expected fraction of time that the process is in state I, corresponds to pi I. And this, of course, proves the claim. So it's important to understand that, it's what are the interpretations of the different quantities that we're dealing with, because interpreting the results is going to be very important when you do applied probability. So when you have actual problems and you want to solve them, it's important that you know how to interpret these terms and the notation as well. Become familiar with the notation. The expected return times. This is something very important. Because the chain is recurrent, then we're eventually going to go back to the state I, let's say, every single state. So RKI
is the kth return time to state I. So I made a little picture here so that we can visualize that. So it takes 3 transitions for R1. The first return time is 3. Now the second return time is 1, 2, 3, 4, 5, 6. So it took 6 transitions in this particular example for the second return to state I, and so on and so forth. So that's the visual that you can have. Now, by construction, RKI are IIDs. And the expected value of the return time is MI. Why? Because we have defined here the expected return time as MI. So this is exactly the expected return time. The expected return time. The RKs are the return times. So that is equal to MI. Now, the law of large numbers now implies that MI is the limit of the average of these return times. So the sample average converges, right? And now we're going to be looking at the following. What is this sum here? Just the sum, just this sum here. This sum here is adding up over all of the return times. So in the picture here, we have, this is 1, the first return time. This is the second return time. This is the third, and so on. And you can see that because I did write the index here. So these n are the total number of return times within little n transitions. So the total number of transitions here is little n. And this is telling me how many returns time I have. So this sum here is basically just the number n. So we are adding all the return times up to n. So that gives us n divided by capital N, which is the number of return times. And now, because n, capital N sub n, counts the number of visits to state or returns, then it turns out that this fraction n divided by n, like we saw just before, is exactly the expected fraction of transitions that the chain visits state I, which we called pi I. And so this basically shows that there is a relationship between the expected return time and the fraction of time that the process is at state I. This is actually, of course, obvious when we have a deterministic process, but it's not obvious all the time when we have a stochastic process. So that's the relationship between in the time scaling. So as an example of how can we use this, going back to the apples, suppose that you need to estimate what the required frequency for placing the orders for apples. Remember that you place the orders whenever the inventory depletes. And so you might want to know if you can have to place orders every month or every 2 weeks or every 3 days. That might be an important thing for you. So in this problem, if the probability that the demand is equal to zero, it's not necessary, but it makes it a lot easier. Then the state xn equals capital K is the only one associated with placing an order. So it's only when we are at state capital K that it means that we placed the order. We placed it the day before, of course, and that will give us the frequency of returning to that state. So it arrives on the day n. This is a positive recurrent Markov chain with finite state space because all states communicate, and it's regular, which is part of the exercise that you did before. So that's regular, and so we can apply the previous results. And how does that help? Well, if we can calculate the limit probabilities, pi k correspond to the long-term fraction of days that we place an order.
And so alternatively, using the result before, we know that we're going to place an order on average every mk equals 1 over pi k days. So that's one way that we can use these results. Now, for the regular Markov chains, which is the ones that we're looking at, we were looking at the limit probabilities. Well, it turns out that the limit probabilities or limit distribution is the unique solution to these equations. These equations 3 and 4 are essential, are very, very important in Markov chains and in the study of Markov chains, and they are called the balance equations. So the proof is relatively simple, just using Chapman-Kolmogorov and the limiting probabilities. So the result that there is a limit probability. I'm not going to go in through that. You can take a look at the resources that I mentioned, the books. But it's important to interpret this. Well, of course, it's important to understand the proof as well. But what is the interpretation of the stationary of these probabilities, pi I? We already have the interpretation of pi I as being the fraction of steps that the process is in state I. But this is another interpretation. Suppose that we start out with this probability, pi, with this distribution. Then, using again Chapman-Kolmogorov, conditioning on the first step, this is equal to this sum, probability that x0 equals k, given kj. So we start out at this probability that, as I mentioned, is pi. So we start out with the initial one, and then we want to move into j. And that will give us the probability that x1 equals j. But this has to be pi j. Why? Because this pi k is the same as here, and this pkj is the same as here, and the equation tells us that this is equal to pi j. So the end result is that this means that the probability distribution after one step is the same as the probability distribution that we started with. So what this means is that the x1 has the same distribution as x0. And then, of course, by mathematical induction, what we obtain is that for this magical probability, what we obtain is that if we start out with this probability distribution pi, then all the time steps, we have the same distribution pi for xn. That is why we call these stationary probabilities, which is, of course, in the title of the slide. And they're stationary. So sometimes when I discuss with the students, I have to emphasize what doesn't move is the distribution. But the process is still varying. The process is going around. It's just the probability distribution, the one that remains stationary. And that's very important. So that's why we call it stationary distribution. So interpretation of the stationary probabilities. When we have a process that has the same distribution, and the visual for this is that if you start out, if you take a look at kn steps in the process, and then you take a look m units of time later, if the process distribution is the same, no matter where you look at it today or tomorrow or in 2 hours, and the distribution is the same, then we say that the process is strictly stationary. If Ci is a cost associated with state I, and we wish to evaluate the long-term cost rate, then by definition, the long-term expected cost is just this equation here. It's the average cost, the average expected cost, and we take the limit as n tends to infinity. But now I am going to take a look at this sum in a different way. I'm just going to add it up in a different way. So I am going to say, well, I want to consider all the values of the cost at every single step. So what I'm doing here is I'm going to say, look, let me put like in one bucket every time that the state is 1. So every time that the state is equal to 1, I'm going to add the same amount, the same cost, Ci. Every time the step is equal to, the state is equal to 2, I'm going to add C2, and so on. So in this way, I basically define buckets for each of the possible states, and I just add the contribution to the buckets every time that the Markov chain visits that particular state. And so it's another way to write it down. It's another way to do the counting, but they are equivalent. And of course, if we take a look now at the second way of expressing that, then we actually we need to justify this, but it is justifiable to put the limit inside. The sum, and the expected value of the indicator function is, of course, the probability. And so this gives me the limit probabilities, which are pi I. So why is this important? This is important because of the interpretation that I boxed here. Long-run averages on the left are the same as stationary averages, which are on the right. And this is the word ergodic. The word ergodic basically means that time averages are equal to space averages, or stationary averages. And they're used in physics as well. They're used in other fields in mathematics, but they're extremely important in here. We will come to that word later on, ergodic. Okay, so there's a counterexample where this equation doesn't, where the limit probabilities are not the same as the stationary probabilities. And this is an interesting counterexample. This is the simplest Markov chain. It's deterministic. It just alternates. It's a binary state. It's a binary machine that only goes from 0 to 1 to 1, from 1 to 0. Now, if we try to use the balance equations, then we definitely can solve these equations. And these equations tell us that the stationary probabilities are 0.5. And the stationary probabilities are well-defined. It means that if we start out with probability 1/2 at state 0, then we are going to be in state 1 with probability 1/2, because we started at probability 1/2 for 0, and so on. And so these are stationary probabilities, and we always have a 1/2, 1/2 probability or 0.5 probability that we are in any particular state. So the stationary probabilities are well-defined. However, this process does not have well-defined limit probabilities, because it's jumping from 0 to 1, 0 to 1, 0 to 1. So if we take the limit on the odd numbers, we hit always state 1. But if we take the limit of these probabilities on the even numbered steps, then we get that the state is always 0. So the process does not forget the initial state, because if you are at the transition, say that this is transition 0. So if transition 1, you're in state 1, but you're always in state 1 in every odd numbered transition. So it doesn't forget the initial state.
And so the exercise for you is, why would the theorems that we saw before that tells us that the limit is the same as the stationary probability, why does it fail? What is the particular assumption that is not satisfied in this counterexample? Okay. So what we have seen now was that for regular transition matrices in finite state spaces, we had the balance equations, and that gave us the solution for the stationary probabilities. And we also knew that limiting probabilities relate to stationary probabilities, and we have that result, that the long-term averages are the same as stationary averages. And that's going to be very important for both my courses, for both courses that we teach. Okay, so the generalization to countable state space requires the concepts of stationary distributions and ergodicity. So I said we were going to come back to this word, ergodic. So a stationary measure of a Markov chain on a general state space with kernel P x dy satisfies the balance equation that the probability of a subset A is basically the integral of the transition from initial state into A, but with respect to the stationary probability for the starting state dx. So it is the same as what we saw before, but in the general notation. And that's what we call a stationary probability. We have seen this before, but I wanted to repeat it here so that we remember that. Periodicity is, a state is positive recurrent if the probability of return to that state is equal to 1, and the expected value of the return time is finite. So that's when we call it a positive recurrent state. And the period of state I is the greatest common divisor of all the integers for which pi to the n is bigger than 0. If the period of a state is 1, then we call it aperiodic. We've already seen an example of where the period was 2, and it could not reach the same state in an even number of steps. So periodicity, like recurrence, is a class property. So again, in this example, which was the counterexample that we saw before, this is a periodic Markov chain with period 2. The states communicate and they are recurrent. However, the chain cannot return to a state except in an even number of steps. So a positive recurrent aperiodic state, what a mouthful, is called strongly ergodic. A null recurrent aperiodic state is called weakly ergodic. And again, ergodicity is a class property. A Markov chain on a countable state space is called ergodic if it is irreducible, positive recurrent, and aperiodic. Now, we are going to deal now with ergodic Markov chains. If Pij are the transition probabilities of an ergodic Markov chain on a countable state space, then the limit probabilities exist, and they are the unique solution to the balance equations. So basically, it's the same theorem that we had for regular matrices, but now the state space can be countable. And the probability vector pi is called the stationary probability or probability distribution of the Markov chain. And I'm referring to the references that I mentioned at the very beginning of this lecture, in case that you want to take a look at that. So in this example is going to be important for my other course on stochastic optimization, and it comes also in the textbook that I am writing. Well, that I wrote. Suppose here that all of the probabilities are bigger than 0. So this Markov chain goes from 0 to 1, and from 1 to 0, but it could return from 1 to 1 and from 0 to 0 at some point. So it's a chain that is moving along. It's also a binary, but it's not deterministic anymore. So the exercise for you is to show that this is an ergodic Markov chain. It's relatively simple. And then what I did was write down the balance equations. It's a very simple example, but it tells you more or less how you look at that. So the balance equation tells me that pi 0 is starting at 0. So look, this is starting at 0 and starting at 0. I don't know if you can actually see the mouse. So starting at 0 and starting at 0. So this is, going to 0. So this is starting at 0, I go to 0, or starting at 1, I go to 0. So that's the way that we read it. The probability, stationary probability of state 1 will be starting at 0, go to 1, or starting at 1, go to 1, with the corresponding probabilities, pi 0 and pi 1. So these are the set or the of linear equations, the system of linear equations, and we have the constraint that they have to add up to 1. And so we can solve by substitution. It's an algebraic problem that is really elementary, and then we can solve for the stationary distribution of this chain. Now, what about the long-term averages? Well, if xn is an ergodic Markov chain on a state S with stationary measure pi and instantaneous cost c, then the limit of the the limit of the average expectation is the same as the stationary average. So what this means is that long-run expectations are the same as stationary averages. And this is what we call ergodicity. So the proof follows the same ideas as for a Markov chain with regular probability matrix, and I'm not going to do it here. You can go back and take a look at that. For an ergodic Markov chain on state space S, same as before, with stationary measure pi and instantaneous cost function c, we have that the long-term averages are the same as the stationary averages. So you might be wondering what is the difference between the previous slide and this slide. Here, this is a limit with probability 1. It's an almost sure limit. This left-hand side is a random variable, and it converges with probability 1, or almost surely, to the right-hand side, which is a number. The difference is that in the previous slide, I'm going to go back. In the previous slide, we have expectations on the left as well. So it's not random variables. Here are long-run expectations, long-run expectation, right? Whereas in the next one, is basically the random variables. So it is the same relationship as when we have the strong law of large numbers or the weak law of large numbers. And so this is very important because, again, we go to the ergodic property that time averages are going to be the same as stationary averages. In the case of simulation, in many cases, we're interested in finding stationary averages, but we don't know how to do that. We don't know how to solve for pi. So we're going to be using simulations, and we're going to be approximating the stationary probabilities or the stationary expectations by long-run averages. So that's the importance, that we can do one or the other. In the stochastic optimization course, we go more in depth in using either the stationary or the long-term average approach, and that can yield very different computer programs.
Okay, so for continuous time. For continuous time, either this continuous time Markov chain or a semi-Markov process, the embedded discrete time Markov chain has transition matrix P. And so if we call Tn the occupation time at iteration of the DTMC, then what we have is that the long-term averages now are over time. Time is continuous. So instead of having sum, we're going to have an integral. How do we visualize this? The way that we visualize this, I'm going to share my iPad now to show you. This is the depiction of a general continuous time process. So the times between jumps, this time Tn, might be, in the case of a continuous time Markov chain, they are exponential random variables. In the case of semi-Markov processes, they might have general distributions. So in general, the Tn, I don't know why I have it read. In general, Tn has a particular distribution that depends on what is the state at that moment. Okay, I'm going to call GI condition on xn equals I. This is in general what happens in those cases. So what happens with the integral? So let me try and shade this integral. So I'm going to try and use a very, maybe using a gray color. Maybe using something like that. So I want to evaluate the integral, which is the area under the curve in here. Because the expression that I have is the integral of C of x of t dt, say from 0 to capital T. That's the cost incurred in there. So what I realized is that for continuous time Markov, well, in general, for a jump process, a process that jumps at discrete times, at random times, I can put this as rectangles. So the area under each of these rectangles is a lot easier to calculate. This rectangle has a base, which is proportional, which is exactly the time t, say t1 or t2, something like that. And then the height corresponds exactly to the value of the function, say c, if this is c. So it corresponds to the function, the value of the function at that time, say x1. I made a little bit of a mess with my notation, so I'm going to fix it. Okay. Yeah. So the height here is going to be, say, x1. So this integral can be expressed in terms of a sum. And in the sum, the integral is basically just summing up the rectangles. So I'm going to just show you the actual equation. So that's why this integral is expressed in terms of a sum. And this sum represents the rectangles. The base of the rectangle is the amount of time that it spends in that state. And the height, well, in this case, is the cost associated to that a particular value. So this is what we are going to use for, this is what we're going to be using for continuous time. That we need to take a look at the time scale and change a little. But basically, if you know the analysis for discrete time, you can carry over for continuous time. This is an exercise that I let you do. In the case of a continuous time Markov chain, we have exponential times, and then you can basically sandwich the exponentials by the largest ones, anyways, but stochastically bounded. So for the continuous time Markov chain case, the above result implies that n of t, what was n of t? Well, let's go back. N of t counts the number of jumps of the chain, which is what we basically wrote in here. So yeah, n of t counts the number of jumps up to time t. So the number of jumps is a counting process. So it is counting the number of jumps that we have, and n of t is basically sandwiched between two Poisson processes with rates minimal and maximal. And that's how we can basically establish that the limit of nt over t exists. It's an AS limit, and the limit is equal to lambda, where lambda is a well-defined real number. Now, for the discrete time Markov chain, the embedded one, the limit probabilities are stationary, and that allows us to, again, look at the integrals in terms of these sums with the rectangles that I just showed you, and that will give us the result that this converges to an expression that involves the pi i's are the limit probabilities of the embedded discrete time Markov chain. And it also depends on the VI. Now, the VI's are the rates or the inverse of the expected amount of time that we remain on each of the states. So there's going to be the time scale changes with VI. And so that's the way to consider the time scale changes. So for the continuous time Markov chain, in general, the long-term average is going to be equal to a stationary average, where the stationary probabilities of the continuous time Markov chain, which I call capital P sub I, are proportional to the stationary probabilities of the DTMC, the embedded Markov chain, which I call pi I. So again, the long-term expected time between consecutive jumps satisfies a particular rate, and this is basically telling us is the expected amount of time, the stationary expected amount of time that we remain on any state. This is basically what it is. Another break, time for coffee. We're almost done. We're going to go into regenerative processes, which is the third part of this talk. And I said this talk is a little bit long, so time for coffee. So we're going to see regenerative processes now. Hope you like your coffee. Okay, so X will be our regenerative process with cycle times Ti. And we assume that X of 0 equals little x is a regeneration point. Now, if you want to take a look at regeneration definitions and everything, I've got another module for that, which we have seen already in the class. So we are going to call A0, it's the time of the, zeroth regeneration. We start at A0 equals 0. And AN is the nth regeneration time. And so the cycle times are the inter-regeneration times, the times in between two regenerations. And that's what we call the cycle times. They're IID, and the TN is basically the minimum time from the previous regeneration until the state hits the regeneration point. Now, in analyzing regenerative processes, one is interested in estimating the expected value of the reach of the cycle length. And this is basically a random horizon problem. And the techniques used are the ones that we did for absorption analysis. So we're not going to go into that. You just basically go back and look at the absorption analysis.
And the other important thing that we want to analyze is the estimation of long-term behavior for some reward or cost function, which is, of course, what we're looking at now. This is a picture so that we are set up on the notation and the terminology. A renewal process, to remind you, is a counting process. It has inter-arrival times tau k, which are IID, and the renewal epochs are AK. So in the picture, I tried to explain the TKs are the times in between two renewals, and the AKs are the actual, well, we call them AKs because we think of them as arrival times. And N of T is the number of renewals up to time T. So in this picture, I basically illustrate the notation, and you can go back in the video if you need to take a look at it, take a screenshot or something. The renewal function of a renewal process is the expectation of the renewal process. It's the expected amount of renewals up to time T. So the proposition tells us that if Ti have density F, so now this is a density, the times are continuous times with distribution capital F, then the renewal function satisfies what is called the renewal equation, which is a recursive equation. And this is the equation that I boxed. The proof of this is, again, by conditioning. As usual with this module on Markov chains, everything is relying on conditioning. So what we have here is the following. We look at this idea that we're going to have, I'm going to see if I can draw this correctly, because I'm not very good for using this. So this is little time x. And x is when the first renewal happened. So after the first renewal, the process starts counting the next renewals. So the process is going to go up, and then it's going to count for the next renewals, and so on. That's the idea of the counting process. It goes like that. I'm not very good with the mouse. So if we condition on the expected total number of renewals, when we condition already on having seen the first renewal, will be the expected value of the remaining renewals. So say from this time onwards, the expected amount of new renewals up to time t plus 1. Because we're conditioning on having observed already one. So we need to shift that. So given that equation, we realize that, of course, this happens, the number of renewals up to time t. This happens provided that this time t is bigger than the first time x. If t is smaller than x, then there are no renewals. The expected amount is 0. So that's basically what we have here, right? And so that yields the result that we have over here. So just integrate over x, and that gives us exactly what we have. Okay, so the discrete time version of the theorem is also valid, and it's in case that the renewal times are discrete times. So we're counting days or weeks or something, then we're going to use discrete time. A renewal process with mean inter-arrival time mu has the property that the limit of the number of renewals up to time t divided by t is equal to mu to the minus 1. So it's giving us the, mu is the rate of arrivals. The elementary renewal theorem states that the limit is also true for the renewal function. Now, this is something that is not all the time true. If a random variable converges, well, if a random sequence converges with probability 1, it's not always true
that the expected value of the sequence or the sequence of the expected values also converges. And so I wanted to include a counterexample that we have seen in other ones of my videos. In this counterexample, we have a random variable xn, which is defined as a function of a uniform random variable. So this uniform random variable between 0 and 1. So given the uniform random variable, xn takes the value n for this random variable smaller or equal than 1 over n, and it's 0 otherwise. So it's a step function, or basically, well, like a reverse of a step function. It's a step function defined on U. Now, clearly, the limit as n tends to infinity of xn is equal to 0. As n goes to infinity, then with probability 1, U will be higher, will be larger than 1 over n. Or rather, for every U, you can find an n such that 1 over n is smaller than that U. And so the xn of U will be 0. And that shows that the limit as n tends to infinity of xn is equal to 0 with probability 1. On the other hand, what is the expected value of xn? The expected value of xn is equal to n times 1 over n, which is 1, plus 0 times 1 minus 1 over n. So the expected value of xn is always equal to 1 independent of n. So this is one case where the expectation of the limit is not the limit of the expectation. And that's why it's very important. The elementary renewal theorem is very important because it establishes that, in this case, we can interchange the limit and the expectation. So the theorem, which is the elementary renewal theorem, tells us that if n is a renewal process with mt, the renewal function, then the limit of mt over t is equal to 1 over mu. So basically it says, in this particular case, yes, it is okay, we can do that. I have a way to explain visually what we're doing. So I'm going to toggle to the iPad in order to show you. So the goal here is to actually to prove that the limit of the renewal function divided by t is equal to 1 over mu. Now, the result that we had before was that the limit of nt divided by t was equal to 1 over mu with probability 1. But as we saw in the counterexample, the fact that one sequence converges with probability 1 does not imply that the sequence also converges in expectation. So the visual is the following. What is A of nt? Well, first of all, we need to get acquainted with the terminology and everything. A sub n is the arrival or the epoch of the nth renewal, right? So n of t is the number of renewals up to time t. So A of sub nt is nothing but the time of the last arrival, the time of the last regeneration from time t. So it's somewhere here before t. That's when the last regeneration or renewal happened. But the next renewal has to happen after time t, because otherwise that would be not the last renewal. So A of mt plus 1 is somewhere here. So this is going to be A of mt plus 1. And this here is A of n of t. So that's what we have. So we're going to call this one variable y of t.
Okay, y of t is going to be the residual time until next renewal. So y of t is smaller or equal than the renewal time, the inter time. This is the time between renewals has a distribution t, has a distribution f. And so this is stochastically dominated by t, this is smaller or equal to that. A t has distribution f, which has a finite mean. And so that means that the expected value of y of t, little t, is smaller than the expected value of that capital T, which is the inter-arrival time. And these are less than 0. And this is for all t. And so now, using dominated convergence theorem, this implies that we can interchange the derivative and the expectation between them. So I'm going to toggle now back to the slides and continue with that. So that's the idea that we have. And so the expected value of the time of the next renewal divided by t, we use this result, which is a known result, and I quote there the references that we have. This is what we're using. We're using that we know that the expected value of the epoch of the next renewal is equal to mu times m of t plus 1. So that's what we use here, nothing else. But then, using the visual that I just showed you with the iPad, that is equal to t plus the expected value of that residual time divided by t. And now we can use dominated convergence theorem because the expected value of y of t divided by t goes to 0. And the fact that the limit of 1 over t is equal to 0 gives us the claim. So this is the way that we can prove the elementary renewal theorem. So the long-term behavior, sorry, I'm going to make a pause because I see that I don't have light anymore. So I'm going to turn on the light. A little bit better, I think. Now you can see my face. All right, so the long-term behavior when we have a regenerative process, well, it's the following. If we have a reward renewal process, again, all of these definitions have been done in a different module, but basically what we have is TI are the times between renewals, and in between those renewals, we have a sequence of reward functions, RI, and they are also IID. So that's what we call the reward renewal process. So the TIs are the times, and the RIs are the rewards that we receive at every cycle. So in a reward renewal process, we define the total reward up to time t as, well, the total reward up to time t. That's exactly what it is. Okay, so this is the way that we define it. NT is the renewal process associated with this reward renewal process. If the expectation of RI is less than infinity, then the limit of RT divided by T, so the rate of reward, is equal to the expected value of RI, so in one of the cycles, divided by E of TI. And of course, because the TIs have an expectation which is equal to mu, then this is equal to E of RI divided by mu. And the proof of that is basically using the strong law of large numbers for Ri, right? The property that n of t converges to infinity with probability 1, and the fact that if two sequences converge with probability 1, to finite numbers, then the product also converges with probability 1. So why is this important? It's important because in the long-term behavior, we can use this for regenerative processes. So a regenerative processes is more complicated than a renewal reward process, but they are related. In a regenerative process with regenerative point X, the cycles are IIDs. And within a cycle, the process can do many different things. The process can move many different ways, but we generally have defined a reward function as a function of the process within one cycle. So what this tells us is that if we have regeneration times that are Ti with arrival times, then the long-term average cost or reward is the ratio of the expected reward by the expected cycle time. And this only depends on one cycle. So it's like all the information on the long term, on the infinite horizon, is contained in one cycle. So in particular, if we define Rn as being the cost function over one cycle, this would be the total reward over one cycle. And of course, the proof of this is related to the slide that we saw before. So what this tells us is that long-run averages are the same as cycle averages. We had already seen that long-term averages were the same as stationary averages when we were dealing with Markovian systems or semi-Markovian systems. And now we see that for regenerative processes, we recover a little bit of the same thing, but it's not the stationary yet. It's not the stationary average that we have in the right-hand side. It's a ratio of two expectations. So this is going to be very useful for both courses that I teach, and particularly we can use regeneration in order to create a statistical estimation for long-term averages and so on. It's called the regenerative method, and it's very useful. So in this example, trains are arriving at a station according to a renewal process. The expected time between trains is equal to mu, and the density is F. Between consecutive train departures, passengers arrive according to a Markov process, which means that the inter-arrival times are exponential with rate lambda. But each of the arrivals might be a group arrival because, people can go there with a family, or they can be there just on their own, or they can be a couple, and so on. Or they can be a school, children from, school breaks or something. So the passenger groups have a known distribution, Pi. In particular, for an example, I just put here 1, 2, 3, and 4, but you could have any numbers. So the mean is, the mean is going to be G. I think I made a mistake here because the mean should have been G. So I'm going to change that. Correction. Yeah. Okay, so the company must pay a penalty of $C to all clients or passengers that wait more than M minutes. So what is the expected penalty rate? How do we solve this? This is an example of application of a renewal process. So Ri is the number of people that wait more than M minutes for the train, because that's basically, it's not a reward, it's a penalty, but it's what we're interested in within one cycle. We're interested in the number of people that wait more than M minutes. So given that the first train arrives at X minutes, the number of arrivals, P is a Poisson, the number of arrivals is a Poisson random variable with mean lambda times X. Now let N sub A be the number of arrivals that must wait more than M minutes. then using one of the propositions in my previous chapters, in my sections of this chapter, then we know that given the number of arrivals, we know that the expected number that arrived exactly m minutes before, or bigger than m, is equal to given p, which is the Poisson random variable, is p times x over m minus 1. So we know that.
Each arrival carries a group of passengers with mean g, which yields that R1 will be g times the expected value of NA, which is the number of arrivals indeed that we're interested in. Now there's two cases. Either the train arrived in less than m minutes, in which case everybody goes in the train and nobody waits more than m minutes. So in that case, the penalty is 0. No one had to wait more than that. On the other case, if the arrival of the train happens after m minutes from the previous train, then there is a possibility that the people are going to be arriving and waiting more than m minutes for the train. So in this case, we can use this result of the conditional expectation of NA that I just wrote in here, and we have this result. So working this out, because the T1, the time between two trains arrivals, we don't know the distribution, but we assume that it has a density f of x, then we obtain this result. And so with this result, we can also evaluate the long-term penalty. Okay, so why are these equations interesting or applicable for the kind of courses that we're dealing with? Well, we will see in our simulation course that if you were to do this by simulation, if you were to evaluate or estimate the penalties, right, for the company, the penalties, then you normally would do a simulation where you code the generation of the train into arrival. Then you generate the arrival of passengers. And then you count each of the passengers that has to wait more than m minutes. And then you do a very long simulation, and you take the average and you try to work out what the result is. You can use the regeneration approach, and for every train, there is a regeneration. So you need to estimate the two expectations, the expectation of the number that have to wait and the expectation of the time between arrivals. Now, the other approach would be use this formula here for your simulation. So if you use this formula here for your simulation, you've partially integrated the number of arrivals that have to wait more than m minutes. That part is the part that you know, because that is the part that you know that has a Poisson a Poisson process, follows the Poisson process. And so here, the only thing that you don't know is, for example, this density, or maybe you cannot integrate this analytically. So the only thing you need to do is either do synthetic data by simulating the arrival of trains, and you basically just evaluate this formula, or you can use data-driven simulation. So you take a look at the actual inter-arrival times for trains in your favorite public transportation system, and you can plug it into this formula. So you will have a statistical part where you're estimating something, but the other part you can already use. Partial. We call this partial integration because it has been partially integrated. So that's the example that we have. When we have a regenerative process, we have again the idea that we have limiting probabilities, and these limiting probabilities are also going to reflect the proportion of time that the process stays at state I. And it also follows that the PI is equal to this expression because we have used the regenerative approach. So this is just within one cycle, and this is the long term. So what happens with regenerative processes is that the long-term behavior can be expressed in terms of the behavior in one cycle. When we have semi-Markov processes, we consider the semi-Markov process on a finite state with an embedded discrete time Markov chain process tilde x. We assume that tilde x is the ergodic with limiting probabilities pi I, and that the holding times for the semi-Markov process satisfy that that these Tn's have a distribution that depends on the current state I. Tau I will be the minimum of return time. So this is basically the return time for the DTMC. And we have a picture which is similar to the one that we saw before for regular DTMCs. So we have a return time, and again, we have a tau 1, tau 2, tau 3, and so on. And so by construction, the total number of returns to the state I is equal to this number here, is equal to that expression. And so this is a little exercise for you. You have to show that these will be renewal processes, and then that you can actually find what is the mean return time. The fourth question is interesting because that's when I'm asking you to prove that this approach using regeneration recovers exactly the same approach that we saw in the first section, where we were looking at long-term probabilities for continuous time Markov chains. So, in summary, when we have an ergodic continuous time Markov chain on a finite space S, then it is also a regenerative process. And in those cases, long-term averages are the same as stationary averages, and they are the same as cycle averages. And so when dealing with simulation, or you are stating what is the optimization problem that you have, you can use either one of these three approaches in order to tackle the problem. Which one is better? Well, you have to wait for my next module on simulation, where we're going to do the analysis, algorithmic analysis of different simulation models. And it, of course, depends on your problem. So this is the end of part 4 on Markov chain. And thank you very much for your attention. I hope that you enjoyed it. Thank you.